How big is the current team working on Restate?
We're still a fairly compact team because we're iterating a lot on the foundation still, which I think works great in a small team.
What is durable async await? Where would I sort of use it in my application?
It's actually it's kind of very, very broad and general, but powerful programming paradigm. Like the idea of Restate and durable async await is that you add durability around certain types of operations, be that, RPC calls between services, external API calls, timed waiting, background work, and so on. By adding durability around these operations, you actually make it very easy to recover from failure. So kind of eliminate a lot of the issues you have to deal with in distributed systems.
Like, are people moving more towards, hey, I just want a managed service that does this for me? Even if I have that safety of open source, but like most of the time I want that managed service. Have you seen a big change over the last, since I think 2009 you were working on Flink, or what does that sort of market look like?
Yeah, that's actually a good question.
Hey folks, this is Alex. Today's guest is Stephan Ewan, one of the founders of Restate. Restate is a durable async await framework type system, right? So if you have some sort of workflow or process you need to do that needs to call a bunch of services, maybe add retries and error handling and rollbacks and all that sort of thing, Restate helps you to do that in your programming language of choice. So TypeScript, Java, something like that, rather than using something like step functions, where you're sort of mixing between your Lambda functions, but also like the step functions DSL. So I thought this was a really great episode on sort of what problems it solves, how it works, some of the distributed system stuff behind Restate that was really interesting. If you recognize Stephan's name, he was one of the creators of Apache Flink, right? So this stream processing framework that really took off with the rise of Apache Kafka. And, he worked on that 10 or 12 years, saw some really cool things, and now has been working on Restate for the last 2 years. So really cool distributed system stuff we talked about here. As always, if you have any comments, questions, guests you want to see, anything like that, feel free to reach out to me or Sean Faulkner with any of that. And with that, let's get to the show. Stephan, welcome to the show.
Hi, Alex.
Yeah, I'm excited to have you here because you're kind of a distributed systems, legend, or at least someone I know and look up to in the area, like based on previous work you've done with Flink, and now have a new exciting project, Restate, that we're going to talk about a lot today. For people that don't know, you can give a little background on you and what you're working on lately.
Yeah, of course. Thanks for having me, and thank you for the kind words. So most of my professional life, I've been working on what became and now is Apache Flink. I started actually out as a database person originally, like working on database like query execution, query optimizers, and so on. After I graduated, we took sort of a lot of the academic work that I worked on, started an open source project, Stratosphere, became Apache Flink. And grew into what is now Apache Flink. So with after a few detours, that happens in like startup and open source land, we sort of settled on stream processing, unified batch on stream processing, and that's what we did there. That's where I spent most of my professional life before 2021, which is when I sort of phased out from the work on Apache Flink and stream processing, and we slowly looked at the sort of like first experiments and steps of what now is Restate, I think what we're going to talk about today. So previously working mostly on like event stream processing for analytics, and Restate, interestingly, is almost like the complementary part of Flink in my mind. It's like event streaming a little bit for transactions. At least that's how it works underneath the hood. It's not how I guess we think about it in the end, but that's at least where it comes from and how it's built.
Yep, absolutely. And I'm sure like Flink was like a really exciting time where like a lot of stuff was moving to streaming with the rise of Kafka, and then like how do we process those, and especially like in more complex ways, and Flink did a lot with that. I guess like how did you get interested in this space, like more sort of durable async await or whatever you want to call that? Like how did you get the idea for Restate based on, and was it based on your work with Flink? Was it something else? How did that come up?
Yeah, I think it's kind of two things that came together. I mean, on the one hand, a little bit just the frustration in general at the state of the art when it comes to just building reliable APIs, like reliable distributed applications. But at the same time, also seeing, we're not the only ones with that frustration. We actually saw in the Flink community a bunch of folks that were somewhat like abusing Flink to build reliable event-driven applications for more like transactional style applications. And that's really not what Flink is built for. You can kind of like make it do a bit of that work because it has a very like high consistency model internally that you can try to sort of like then connect other systems and make it kind of coordinate distributed transactions. But it's not actually great. It's a little bit like trying to abuse your OLAP database or transaction processing. But it kind of showed us that apparently there's nothing really there. So folks are turning to these kind of solutions, that they're using systems not built for these type of problems. And when we said like, okay, we have issues with these problems. Other folks are abusing our analytical technology for transactional processing because they seem to have these problems. Maybe there's something there and we should start looking at that.
Yeah, absolutely. So, for those that aren't sort of aware of this space and Restate, what is it? What is durable async await? Where would I sort of use it in my application?
Right. So it's actually it's kind of very, very broad and general, but powerful programming paradigm. Like the idea of Restate and durable async await is that you add durability around certain types of operations, be that, RPC calls between services, external API calls, at timed waiting, background work, and so on. By adding durability around these operations, you actually make it very easy to recover from failure. So kind of eliminate a lot of the issues you have to deal with in distributed systems. Like how do you figure out if, for example, you're updating different systems, you want to keep them in sync, and some stuff has happened but the other not, and you have to kind of figure out what went through, what didn't. How do you make sure you don't re-execute the previous parts, but you always make sure and eventually also execute the parts that didn't initially go through and so on. So you get a sort of consistent view in the end. It helps with all sorts of those problems. So anything where you sort of talk to different systems, where you need reliable background work, reliable process-to-process communication, it's kind of geared at solving those problems. And the core idea is like very lightweight durability added sort of to the. If you come from a TypeScript world, the easiest way to think about this is like the promises. A lot of this is written like in like async await style. You make like a call to another system, you await the response and so on. And then around these like async await operations, you add a lightweight form of durability that helps you recover.
Awesome. And what are people currently using to solve these types of problems? Like, is it just sort of certain patterns in their application? Are there other tools that help them with this? Or like what sort of tools are people putting together to solve this?
Yeah, I think there's different ways that folks approach this right now. I'd say a lot is just I'd say not solving that specific problem, but just trying to work around it in a way, trying to like design applications in very specific ways so you can try and make certain pieces idempotent and then just like retry forever until it goes through and just hope like everything else sort of cancels each other out, which sometimes works, sometimes doesn't. Sometimes folks use workflow engines for this. I think this kind of problem, making sure stuff happens, runs to the end, all steps get complete, is kind of a classical kind of workflow engine topic, actually. It's just that there's, I think, a very big space where you do want this kind of behavior, but it's not such a big and heavyweight sort of thing. It's maybe just a lightweight process that orchestrates between two other processes so that you don't actually want to pull in a heavyweight workflow engine. And that's when it actually starts. And you have to kind of come up with all of your own sort of transaction protocols and sort of retries and deduplication semantics and so on. So I would say it's kind of a mix of both. Like if it's a sufficiently complex process, maybe you pull in a workflow engine. If it's kind of a lightweight process, you kind of try to build your own protocol. Maybe there's something in between where folks use like message queues, SQS, Kinesis, Kafka, and so on to sort of like schedule these tasks in a more durable way. But also that kind of still involves a lot of like your own design of like requests and how to duplicate them, like how to tie different IDs and tokens together and so on. So yeah, all in all, I would say it's a lot of like roll your own. And this roll your own is, I think, tougher than it initially sounds. Like I always am surprised at the corner cases that come up that are not that easy to spot in the beginning. I think that's why the roll your own ultimately is something that has many problems when folks do it, and it's also something that increasingly more and more folks realize is actually very hard and try to avoid, and that they try to look at different solutions. So I think that's also part of why workflow engines recently have become more popular, and you can see this, for example, in the rise of popularity of step functions and so on.
Yep, absolutely. So just to put it in sort of an example everyone can understand. The example I think of, I think it's in your docs as well, is just a checkout workflow on an e-commerce site, right? Where someone hits checkout and now you need to, decrement the inventory, maybe you need to process a payment, queue that up for at least some sort of order record. You need to hit a bunch of different systems or databases or things like that, right? To make this happen. And like you're saying, you can just sort of hit them in order in your application and maybe wrap them in retries and sort of hope it works. And occasionally one falls through and now you got to manually fix that. Or now I think in the world I see a lot of step functions wrapping this around that, which has its own sort of, pros and cons around that sort of thing. I think that'd be the workflow solution that you're talking about. You're talking about the adding durability to this. What does that specifically look like when you say, Restate sort of adds durability to this? Where does that durability comes in? Especially I see Restate integrates with Lambda, which I don't think of as having durability or anything like that at all. So what does that actually look like to add durability to this process?
Yeah. So the way it works in Restate is you have basically two parts. You have a small SDK and you have a server component. You can think of the server component a bit like something in between, like a log database, very lightweight workflow engine. It's a stateful component that maintains a durable log internally. It also acts like a proxy for a lot of things that happen in your application. So, for example, if you're again, the simplest way of using Restate, and you're writing sort of an RPC handler, and you want to say, okay, make that RPC handler durable for me, you'd actually register that at Restate and say, Restate, become the proxy for this one. Then, as you actually call this through Restate being the proxy, you have this connection between your RPC handler and the Restate server, and it basically tracks many operations. Like if you do an external API call and you wrap them sort of in a Restate operation, or if you make a call to another system through the Restate SDK, it wraps those operations in an internal sort of a durable journal entry that it commits, but it also remembers sort of how this connects to the application. So it first of all records internally that this operation has happened, and then it also understands how to complete that operation when it's done and send this back to the process. So in case, for example, something fails in between kicking off the RPC and receiving the response, or maybe if in the case of Lambda, you explicitly want to go away between sending the RPC and getting the response because you don't want to wait, it understands how to connect the response back, complete that promise, and then give it back to a new invocation of the function, and then say, okay, now continue from here now that we've completed that promise. So in the end, you program in a sort of familiar sequential sort of request response RPC, or make an API call, await the response, and Restate is kind of the proxy for these promises, and sits kind of as a middleman in between, records the creation of them, the completion of them, and facilitates sort of the recovery in case something happens in between.
Gotcha. So all that traffic is going through this Restate server component type thing, which I want to talk about architecture for that and what that looks like. So, but all that traffic is going there. It's routing it to the other services you have, which could be Lambda functions. They could be, Kubernetes based service or whatever it is, just some sort of endpoint that it can then handle it. And it's sort of tracking the status of those as it goes through there.
Yeah, that's right. It's not unlike saying, you're invoking other functions through an event. You can, for example, if you talk Lambda to Lambda and so on, you can do that by enqueuing an event in SQS or something like that. It's not unlike that. It's just that you're not actually writing it like that. You're not writing okay, I want to enqueue an event. I need to sort of understand that I make sure I enqueue it only once. I do enqueue it in case something fails. I don't need to worry about the recovery and the sort of deduplication that kind of connects the recovery and that enqueuing and all of it together. Because Restate kind of sits a little different between the components. You don't actually explicitly enqueue events and so on. It's really the SDK that kind of captures this, creates and kind of logs it to the system in the background and always connects it like with the current execution and retry and so on to make sure things happen only once and don't get duplicated. So in the end, yeah, you can think of it. It's like an event-driven system. It's like an EventBridge or SQS or something sitting between applications, but like you program it in a much more high-level way, so that it in the end looks like, yeah, you're really programming sequential RPC with like durable promises.
Gotcha. On that sort of, you mentioned EventBridge, does it have like the sort of decoupled producers and consumer type concept like that you would see in EventBridge, where like a producer might just fire something into EventBridge and then whoever, wants to be subscribed to that thing? Does it have that sort of concept, or is it more sort of intentional RPC, or at least like, message passing type stuff?
Yeah, it is, at least in the current version, more this in intentional RPC. Though with a few like nice additions, like you can think of this as request response, like one way kind of fire and forget, but like with at least with reliable like accepting and delivery semantics. You can use this to also like schedule events and invocations a bit like you can do with EventBridge, that you say, okay, hey, this is maybe this is an invoicing process that happens only once per month. So I wanna schedule this for the next month, and then when this happens, let me schedule it again for the next month or something like this, or just on a periodic timer or so. So it's not a classical PubSub. I mean, there's no reason for us to not expose that at some point, but at least at the moment, it's not a PubSub in the way of here's a bunch of producers and a bunch of consumers. It's really more a facilitator for really direct RPC style communication at the moment.
Gotcha. Yeah. And it is interesting. I see a lot of people use EventBridge for sort of that direct messaging, even though it's like not quite as much for that. And they just like don't know what other abstraction to use for that. But it's interesting because like, it seems like Restate can replace a lot of other AWS primitives that I often use. Like I thought of it initially as like, hey, this sort of is a step function replacement, but it also sounds like SQS probably using less of that if I have something like this. EventBridge scheduler, like you're saying, if I need more like dynamic scheduling, do this in 15 minutes or 3 days or at this particular time, I can do that with Restate. So like it replace even like some of the DynamoDB streams usage I use, like where often I have sort of like the dual write problem, right? Where you want to like write a record to the database and then enqueue a message or do something else. And you can either do that in your same process, which is kind of finicky, or you can write it to the database and then process it asynchronously with Dynamo streams or whatever, change data capture. But now Restate can sort of help handle that specific issue.
Yeah, I think that's right. And the way I would think about it is the following, right? Like so many of these primitives exist because there's so many different challenges you have in a distributed application. And I mean, distributed application doesn't even mean like fancy distributed. As soon as you have your own process and you're talking to one other process and maybe a database, you have a distributed system, right? And you have a lot of the problems already, right? And there's so many classes of problems. You just mentioned dual write problem, right? Then there's the problem of so making sure you have like idempotency, making sure you even have recovery. There's the issue of like building circuit breakers and so on. I think so many systems exist. And then there's of course sender and failure decoupling, right? If you're doing an operation that takes longer on the receiver side, you absolutely don't want this thing to be completely lost if the connection sort of breaks or the sender fails or the receiver goes away in between. You really want to decouple all of those things. And because there's so many individual things you actually need to worry about, I think there's so many products and so many solutions, right? And one of the ideas of Restate was to take a step back and look at this in just in a slightly more fundamental way. Like, what is really the thing that causes so many of these issues? And then build like a very sort of broadly usable set of primitives for that. And I think because of that, it kind of like says, okay, like if you use it, you probably need a bit less of that and that and that and that and that, because it helps actually with a bunch of problems, not just like with one problem. Yep, absolutely. Okay, so I'm sure you've paid attention to this space better than I have, because I mostly know sort of step functions. And if I could sort of compare and contrast step functions with Restate, it would be Restate lets you sort of stay in
in your, TypeScript land or Java land or whatever your programming language of choice is more when you have these sort of distributed things going on, rather than if you're in step functions, you might say, hey, there's this first step, it's going to do something and it's going to throw an error or throw some sort of result. And you're sort of kicking between your programming language, maybe in a Lambda function or something else, and then back to like more like an infrastructure as code or some sort of DSL for like processing through the states. So that would be like the difference, I'd say, between restate and step functions. What about some other ones I hear about, like temporal came out of Cadence? Is temporal like in the same category as restate? Is it a different type of thing, or like how does that sort of compare, contrast?
Yeah, I think that's interesting. It definitely is in a similar category as in, and Temporal is a durable execution framework. I think that's how they at least used to call themselves also for a long time. Restate definitely, durable execution is a core part of what it does. I think Restate takes a bit of a different approach because it doesn't look at, okay, here's a durably executed workflow and now you try to connect everything to that, but it really tries to take more of you could say microservice architecture approach, or even a slightly simpler approach to that, where Restate's not specifically about building workflows, it's about building like durable event handlers, durable RPC handlers, stateful RPC handlers. Like there's a component that actually lets you like attach state directly to the handlers and like keep that sort of transactionally consistent with the invocations. And I think that gives it a bunch of like different characteristics than Temporal. And while I think there's like some overlap, I think Restate really is a bit more general and more towards the general distributed applications rather than like in the specific workflow category. I mean, that being said, you just said that you compared mostly to step functions. I think that's actually a great category because like to my mind, step functions it's like workflows, but it's a little bit more. You don't think of step functions necessarily as just like the long running sort of workflows for days with like human tasks in the middle. You can also use that for like fairly like low latency and fast orchestration tasks and so on, right? Like, and I think that's also kind of a category that Restate is in more. It's not just heavyweight workflows, it's also like very lightweight, fast distributed coordination orchestration.
So you might use a restate. Do you call it like a workflow, or like what do you call like a restate? If I have a handler that uses that, what would you call that?
It's actually interesting. We're still debating what's the best way to call it. At the moment, we just call it like a durable handler.
Processor. Okay. So if I might have a durable handler that calls a bunch of systems, but that could still be in the synchronous path of a request from a client or something like that goes through a bunch of different things. I could still get a synchronous like HTTP response back from my client sometimes when using Restate.
Yeah, that's right. So the individual operations in Restate, like we're paying a lot of attention to building it in a way that they are quite fast, like take at least very low latency. So when you for example have different processes, even if they both run on Restate, and let's say you're kicking off one handler by an RPC call from the outset, you're making this call, another one, and so on, you're waiting on a response to get back, call another one, like it's in the order of like milliseconds, like every time you're hitting the different processes. It's actually built to be like a very fast just append to a log, and that's it. And that allows you actually to do a bunch of steps still in the synchronous path, which is really where we want to see this thing go, because if you actually have this ability to add workflow style durability to handlers with low latency, you actually move a lot of things that are sort of not possible to where it's not possible to use workflow engines for them, because they tend to just take too long, right? You actually make it possible to use that, and you all of a sudden have a big class of use cases of type of patterns where you can all of a sudden benefit from this like very, very nice tool that makes a lot of these problems just go away that you couldn't before, because it was like latency prohibitive to use those type of tools. So maybe one interesting example is it's the one that we also that we're also using on our website or in the blog post is this classical step functions demo, like the holiday reservation, where you have a process that it takes care of like orchestrating everything, talking to like flight reservation, car booking, hotel reservation, and so on. Also implements all the control flow, like what if something goes wrong, implements the sagas pattern actually in the end, and undoes the previous steps in case an error occurs. And you can actually run this like in a synchronous response path, like assuming at least every individual service is reasonably fast in responding, then like the restate component adds very moderate like latency overhead to this.
Yep, very cool. Okay, so I want to know more about, I think you call it the restate runtime, but basically like the server component that's handling this flow between that you're serving as a proxy, handling the durable state and things like that. Like what does that component look like?
Right. So the server component, just to quickly recap, is the one that kind of sits sort of as an intermediary between all the different points, and it's the one that's responsible for making sure that you can actually program sort of distributed programs that execute, recover from failures in like an almost simple sequential RPC style. So kind of pretending failures don't happen. You can embed the control flow, the failure handling flow, just like that. That's actually in a way the biggest difference also to step functions, if you wish, right? Like and on the step function side, you basically go and say every individual bit that you where you let's say care about but let's say between two parts where you care about like failure handling and say, okay, once this part is completed, like I have to make sure it doesn't get re-executed and I need to sort of like have the results of this durable committed before I'm starting the next thing. Every time you have this, you kind of pull it apart into different pieces and kind of orchestrate it with something like a step functions flow across it. And in Reset, you don't do this. In Reset, you basically just write the control flow down and you let like the durability of the individual steps take care of it. And the runtime is the piece that sort of sits as a proxy or sort of sits in the background and sort of accepts the stream of messages that like facilitate the communication, that sort of like persist the creation of the promises and so on. What it looks like is when you use it yourself, it looks like just a single binary that you bring up. It's actually fairly compact. You just like start it. It has everything it needs in there. A log, like a state storage engine, sort of registry for schema functions, communication, and so on. So it's a fairly compact bit. Maybe it feels a little anachronistic, but then at the same time it doesn't. I think there's a bit of a swing back of components being built that way, like from everything is just a set of custom resource definitions on Kubernetes. We're going back to like, okay, things actually are sort of like standalone binaries that do their thing without requiring 100 other things. So Reset is also that. It's a simple thing. You start it runs there almost like a lightweight sort of database. And then in your applications, you embed like the simple SDK, almost like the database client. You connect to it. And then it kind of acts as your proxy or broker for the communication. That's kind of how it works. So in that sense, it's not actually wrong to think of it as it kind of takes the place of maybe the SQS queue between your services, or it takes the place of like the step function coordinator. But what it looks like internally is it has a very specific architecture. It's a log-based system with sort of an engine that sort of asynchronously interprets commands, materializes indexes over the log, and handles sort of the network communication, the invocations, event dispatch, and all that. I'm always trying to find like simple ways to compare it, but you can think of it a little bit as it's a log. It's a bit like a Kafka or Kinesis log with sort of an event processing application built into it that works on the events on behalf of your application, and then basically only talks to your application like in a very sort of high level way, as in, okay, I've done this for you, I've got a response here for you based on that, and it kind of keeps sort of the ground truth of everything that's happening in this like log and command processor. And that really is kind of how also the simplicity of the correctness model, how it happens, because it kind of makes the application mostly just say what should happen and let the sort of command interpreter make it, or the central log make it happen for you, and then sort of like listen to the response for that. And that gives you this sort of like nice correctness out of the box experience.
Okay, sounds good. So trying to understand it, and I definitely don't know as much about distributed systems as you, but you've got this server component where it's sort of receiving these RPC calls, or maybe even like state setting calls, right? Like if I'm a handler, I can sort of set some context or just like little bits of state for that particular function. It'll handle that. It's going to persist it to that durable log you have. Also maybe like some materialized data, like in, I believe like RocksDB, just to make that like a little more queryable and stuff for resuming stuff. And then also proxying that to two different other handlers you have. Am I understanding that correctly?
Yeah. Yeah, that's right. Let's maybe walk through this as an example, and really show what happened in the runtime. Then we can also sort of explain a little bit why it is built the way it is. So let's maybe take this like holiday booking Sargas example for a moment. So if we're the general sort of like the main function that has the workflow that talks to the different services, right? So we've been sort of executed proxy through restate. So restate has an sort of event in the log that says, okay, well, I want to run that workflow. That part's not too unlike, I think, how most other workflow engines work. Like they write it in the write-ahead log. So restate kind of dispatches that, and then as you go through it, as for example, the code says, hey, I need to now talk to the, let's say, flight reservation service first. It basically streams an event in the background to that server component. And the first thing that server component does is it actually appends the event. And then it has sort of established the ground truth. Okay, we've reached that part of the program. We've sent this bit. So it first of all is just like a very sort of cheap append to the log. But what happens at the same time is that there's like a process that so indexes these events. It establishes the relationship that this event that we just appended is actually part of it's kind of related to the original workflow execution, because it's an event that came out of this, and it sort of attaches this to a recovery journal for that workflow function, for that handler. And anytime something goes wrong, it can actually use that to reinvoke it and say, okay, do your thing again, but when the next time the promise gets created, it actually sees like from the recovery log, oh yeah, that promise actually is already there. It might not be completed, but at least it's there. So let me actually not send this again because I already have that. At the same time, at some point, also the other service is going to respond with an event that completes it, and then all of these are really just like they're meant to be very fast appends, so we actually get that durability very fast. But then it's sort of again indexed into, okay, this is a completion for this specific original RPC event. So let me kind of attach it to there, like augment the original sort of promise with its completion result, failure or success, and so on. And then if it's still executing, just forward it to that process. Otherwise, keep it there, and the next time it executes, it can be sort of resupplied as a completed promise to the executed function. So that's basically what I would say those are the 2-3 most important pieces we have in the system. It's like this log built for like fast append, fast durability of operations. RocksDB is more like an index that sort of tracks the relationship between events, and if you wish, like state. That you attach to a handler. It's just like a specific sort of event that then gets sort of attached to the identity of that handler, a certain key. RPCs are really specific forms of event that get attached to like an execution of a handler and so on. That's the second part, and the third part is the component that sort of manages the communication with the services. Maybe a quick note on why did we build it that way. So in theory, we could have also built it as we use Kafka as a log or Kinesis, and then we store things in DynamoDB and so on. There's a bit of I think maybe let's take a step back and look what that means like from a distributed systems perspective, if you actually do it like that, let's just take, let's say Kafka and DynamoDB. If you actually piece together those two systems, what you ultimately now have is you have actually two logs involved. You have Kafka as a log, and then DynamoDB, every database's core truth is its own write-ahead log. That's where it records things that by its definition have happened. Now, if you say, okay, I'm writing an event to Kafka and to DynamoDB, you have a problem now. You have actually two logs that you need to keep in sync, and you need to kind of implement, if you wish, at least a poor man's transaction coordinator that says, okay, maybe after I've appended it to Kinesis, if I crash, I have to like look at this and see, have I moved it to the other system or not? Like, what if I do find something in that other system and not here? Like, you're already at I would say the core of where most of the distributed systems complexity comes from, like keeping different components in sync, right? The beauty, I think, of the way that we've built this with just like one log and everything else is sort of an asynchronous process that follows this log is exactly one ground truth. Like something is appended to the log or not. That determines by Restate's perspective, did it happen or not? And everything else is a view that follows, and it's kind of very easy to let that view follow consistently, especially if it's like the same component that manages it. And that actually gives us two very, very nice characteristics. First of all, it's a fairly easy thing to make it correct, because whenever you have different systems you need to keep in sync, you're going to hit so many corner cases over time where you need to like have a more elaborate protocol that deals with that. We don't actually have that. Like it's fairly simple to get it correct. And one of the interesting outcomes of that was that like fairly early versions of that system, when we like really stress test them with very heavy sort of like chaos monkey style tests, like had complex logic that cares about consistency and correctness and just like shoot things down, introduce disk crashes and corruptions. Like it's fairly hard to actually make it trip up for a very early, for the early stage that it is, it's pretty resilient. That's one of the like really nice outcomes. The second one is it's also fairly easy to operate because it doesn't run the risk of like, okay, what if like the log actually executes faster than like DynamoDB can take the inserts or so, or like, yeah, what if this one has a compaction and then the other one has one at a different time and they kind of both stall each other out and so on. Like it's fairly, because we care so much about the system being easy to operate, like this architecture lends itself to that very much. It's an architecture that has comparatively few knobs and sort of things that can drift apart from each other. That's what we liked about it a lot. And that's why I decided to do it that way. Okay, that was a very long speech.
No, that was great. And like, yeah, just thinking as like a user of a piece of open source infrastructure, if I know I have to go set up, not just this infrastructure and start running this binary, but like, send in these credentials to this DynamoDB table and this Kafka cluster and all that sort of stuff. It's just like, okay, now I'm managing three things and I don't really have that much control over how they interact. It's just nicer to have that more in that single binary type situation.
Exactly, because maybe we haven't actually said this before. Like the way we really want to get the system to users is we're working on a managed service, and of course we want to have a service that's easy to operate for ourselves, but we really also want to we're publishing this as an open source system. We want folks to be able to run this, if you want, themselves at least in their own accounts and so on, if they need to, with in an easy way, like not in a way that doesn't require too complex operations. And maybe that's something we sort of learned a little bit from our previous work on, like in the sort of space Flink and Kafka and all the other systems that connect to that. It's very easy to get into trouble, even if you think a system is like super well behaved. There's just like every system itself makes sense, but there's just different assumptions they make every time they interact, just slightly different intervals in which they refresh their credentials, slightly different ways in which they like use their like when they have their burst and how they react to burst and so on, how they can stomach that it's very easy to get those combinations of, if you combine many complex systems, you have something that is very easy to trip over, even if each system in itself is actually fairly well behaved. And that's kind of what we wanted to get out of that situation. That's why we're putting it into one.
Yeah, based on your experience with Flink, and especially with Flink for a long time, and now talking to customers, I'm sure with Restate, like, are you seeing a change in how people, like, are people moving more towards, hey, I just want a managed service that does this for me, even if I have that safety of open source, but like most of the time I want that managed service. Have you seen a big change over the last, since I think '09 you were working on Flink, or what does that sort of market look like?
Yeah, that's actually a good question. So definitely the acceptance of managed services is way up there, and also the wanting to use a managed service. Absolutely, for Flink when we started was all prem. In the end, it was so many folks asking for managed services. There's not such a thing as the managed service, right? Like there's so many different paradigms. There's like, you can have a multi-tenant managed service that is shared by many users. You can have a managed service that has like dedicated resources and has an isolated processes and per tenant. You can have a managed service that runs some part in maybe the vendor's account and then keeps a lot of maybe parts of the control plane or some very low level storage primitives, and then runs the sort of sensitive parts in the user's account to make sure like the let's say at least the unencrypted data or like the direct connection to their application services and so on doesn't leave their account and so on. Like there's this wide spectrum. So it's kind of, I'd say it depends on what kind of user you talk about. The long tail is more on the like really fully managed side of things, but there's still a lot of big use cases that need at least the dedicated clusters that like these clusters to run in their own accounts and so on. So like building to make this easy and possible is, I don't think it hurts, to be honest.
Yep. Okay. I want to backtrack to something you said a while ago because it was in my head. So you're talking about the process of what's happening on the server. Like if I want to call some other service, it's going to sort of write that log event. And then, when that service responds at some point, that'll have a different event and mark that. So does that mean like if I'm using Restate, like sort of both services have to be sort of using Restate for that sort of thing? Like, can I use Restate around calling an external API that I don't have control over, or even calling out to like Postgres or something like that? That's not going to be sort of fully integrated into that Restate ecosystem, or is it more just like internal RPC type stuff? Is it like that's the core of what you're doing there?
Yeah, I think you can use it for all of those things. I would say the simplest thing is, you can make it as simple as a one-step workflow, right? Let's say you have something that comes. Maybe it's something you even schedule for later or so. That's why you're piping it through a system like Restate, and then it does exactly one thing. It wants to commit that. It wants to acknowledge sort of that this happens. Done. So you can use it for that. Like Restate allows you to basically wrap like any type of API call in a side effect instead of a managed promise, if you wish. And then that's that. And I think a lot of the like simple examples kind of look like that. You have one durable handler with a bunch of calls that it makes, to other services. That is it. And that's totally fair. I think the interesting part is if you start going beyond that, if you say, okay, maybe this one handler I have is there's a bunch of other sort of like services that it needs to interact with. Let's say that you have that example of the checkout process, right? It calls maybe an inventory service to decrement accounts. It calls a payment service and so on. And when you start saying, okay, hey, I'm not just using Restate for this one thing, but I'm also using it to sort of like I'm also using it as part of not just the checkout flow, but let's say also the inventory service and so on. Then you kind of get a few additional benefits because now you have sort of both sides managed by Restate, and that means you get kind of get exactly one sort of communication between them, or think like retries, idempotency, all of that. Just completely for free. You can actually pretend they talk in a completely like reliable exactly one's manner, because both ends are on a proxy to the same system, and it can kind of work its internal magic to make this nice. You don't have to do this. It's completely valuable for one service, but like when you put in onto it a few more services, you get a bunch of additional benefits, and I think that's where over time I think people like to go.
Yeah. Okay. Tell me about that exactly once and how that works, because I know like there's some blog posts on, hey, exactly once is impossible and things like that. Like, what do you sort of mean by exactly once, and how does Restate solve that particular issue?
Yeah. So I think that's good. Like, exactly once is a very controversial term. I think exactly once, in terms of like invoking a service exactly once, is not something you can realistically achieve, like by laws of logic, math, and so on. But that's also not what you really need. You need the effects of the service to happen just once, right? That's kind of what I think exactly once always has been about. When you talk about it in stream processing, or like even in the context of database transactions, you never talk about kicking something off only once. You talk about it materializing its effects once and only once, right? And it's often achieved like by a combination of sort of like retries and idempotency, or like some transactional commit protocol on the bottom, which at least has one retry and idempotent step as well in it usually. So I think that's really what it's about. Like, if you have two services, one is sort of sending its event. It's important to understand like the sending from of an event from one service to the other is anchored like in the durable execution, in the deduplication, and so on. So when this is sent, it actually goes as an event in the background to the restate server, which appends it to the log, and then it has this like single write that acts both as, okay, we've created the promise, but also we have work to do here, namely like send that message to another service. So we've kind of established an endpoint that sends an event that deduplicates on retries. Like, if that handler fails, it recovers and goes through there and says like, okay, I have actually created the promise. So creation and sending happens in a deduplicated manner. On the receiving side, it's the same thing. Like, you receive it, you invoke the handler. You might invoke it multiple times if failures happen in between there, but every time you kind of invoke it, you understand the effects that already happened. You kind of give the completed promises for these effects back, and eventually you conclude it. So what you will not ever see is the event being sent out twice, or resulting in sort of like two individual invocations that don't share each other's partial progress. I think that's what it boils down to in the end. And that's, I think, really all you care about. That in the end, it kind of means that like one or two invocations happen as part of like a retry strategy. It doesn't matter. It matters whether you apply the effects.
Doesn't change the result.
Yeah. Multiple times.
Yep. Very cool. Okay. And then, so going back to this runtime thing, if I have this server, am I running like multiple instances of it for sort of like replication and better like durability and things like that? What does that sort of look, and for scalability as well? Like, what's a common configuration? Am I running 3, 5, 7 of those, or what's that look like?
Yeah. That's a great question. So at the moment you're running one, because that's the version that is out there. We're working on the distributed version where, I think you would eventually run as whatever your load sort of requires. I would say starting with 3, one in each availability zone of a typical region. So that, I think that would be like what we would probably recommend in the future if you want to run it yourself. At the moment, it's one process. It basically persists its log durably by writing it to something like EBS. So the simple thing you can use right now is we actually have a few tools around this, like CTK constructs and so on, that would basically deploy it exactly as like an either EC2 instance with an EBS volume, or just saw the release of like Fargate EBS support and so on, like a Fargate task with an EBS volume and so on. Those are like perfectly fine deployments. It actually doesn't really matter even if your task is that long lived, as long as it really only matters if the log survives. The log has to be durable. That's why it has to be an EBS. Like, wherever you run, the rest doesn't really matter. And in the future, we want to take care of that replication ourselves for a few reasons. Like, cost effectiveness is one thing, but the other thing is like cross AZ durability. It's not something EBS gives you at the moment. So and S3 is too high latency to write. Still, the low latency version is again only single availability zone. So also doesn't help there. So that's why I think we're working towards our own log replication at the moment.
Gotcha. So in some future where you're doing replication, does that mean you'd move away from EBS and do like more instance-based storage, or would you still be using EBS and relying on some of those guarantees there? Like, I'm kind of curious on how those trade-offs manifest for, distributed systems builders like yourself.
Yeah, that's actually a very interesting question. I think that I would say it depends just a little bit on your risk appetite. I think it's very related to the question whether you should fsync a log or not, right? Like if you don't fsync your log, for example, you're basically relying on instance memory or so for a time being. Let me put it like this: like, what are the logs really for in a modern architecture? At the end, you very quickly want to go to durability through something like S3 for the majority of your data. So you get latencies out of that in the like tens, hundreds of milliseconds if you go to the cross AZ1. Like the 99th percentile here really matters. So it's probably more like 3-digit milliseconds in many cases. So in a way, the most important thing you have to bridge is the latency until that point has come, and maybe a bit more, because you don't want to, depending on how much you write, you want to amortize kind of costs into bigger writes, right? So you don't write like two small chunks. So you kind of have to bridge just like this small bit until you've gotten enough data and like enough of a latency window that you can flush it out to S3. This is what you have to bridge. This is what the replication is for. So, is just like replicating to instance storage or even to instance memory good enough to bridge that, right? It kind of depends on what failure rates and what kind of failure scenarios you assume. Most of the time you'll probably be right replicating to memory. You'll probably be good replicating to disk. If you actually want to replicate to something like EBS, even in the small window, kind of depends really what class of failures you're addressing. I've had this discussion a while ago with some Kafka people that I asked them, like, would you fsync or not, and what is the sort of the worst thing that you lose if you don't fsync? And they said the worst thing that we typically lose, or the cases where not fsyncing usually matters, is somebody accidentally deallocating the entire deployment. Like, you run it on Kubernetes, even like with multiple sort of like failure domains and anti-affinity and so on, and you don't ever lose data because all of your AZs go down at the same time, but you lose data if some administrator unfortunately deletes the deployment, because then everything goes away in the small window before you kind of can flush it out to the more stable storage. And that's why it might for some people still matter, I think, to persist it to something like EBS still, because then you still get to defend against those scenarios. If you're kind of happy with sort of the math around failure rates and you trust kind of your ops team to not take down all AZ deployments at the same time within the same second, maybe you are okay with the sort of cost benefits of just replicating to memory. I'm not sure if there's a one answer for all.
Yeah, it's a tough one, like right on that edge there. So is Restate currently, flushing stuff to S3 occasionally for that more durable stuff and getting stuff off just regular disk?
We're not doing that at the moment, but it's something we're working towards which is incidentally also something why for example we really like having RocksDB in there, because if you actually have a replicated log, the sort of LSM tree design is actually a really interesting one for storage engines, right? Because it has this like hierarchical immutable artifacts that are asynchronously merged. It lends itself really well for like storage on something like S3 is good for immutable artifacts, right? For something like that. So it's another reason why we'd like to start that way.
So you're flushing not just, or like you might flush like the RocksDB segments and things like that to S3 as well as like the log segments. Is that what you're saying?
Look, we might. We're still in the process of developing this. It could be very well that by the time we do this, it's not actually RocksDB anymore, but it's like a different sort of a different storage tree and so on. But like conceptually thinking, yes, that's where we would move to. Yeah.
Yep. It's been fun seeing like the sort of all the S3 stuff that's happening with like data systems. Like I talked to the Warp Stream people recently and just what they're doing with S3 and just like how it's sort of changing data infrastructure in a lot of interesting ways, like you were talking about. One thing I thought that was interesting too in the docs that I was looking. So you mentioned RocksDB is sort of your state storage, but it's actually, you can actually like query it via Postgres, right? You expose it like basically via Postgres. What's going on there?
Yeah. So the so RocksDB basically is our state index, but not just state, right? Like it's I actually just like try to emphasize this. RocksDB stores sort of the relationship between all events in the end. Like here's an event that corresponds to this workflow execution. Here's an event corresponding to that RPC invocation of that thing on restate. Here's an event corresponding to that like committed side effect or so to another system. All of this is events that get appended to the log, but then indexed sort of in RocksDB. And by making this queryable, you can find out a lot about like what's going on in your application, like what's currently running, who's kind of calling whom, who is waiting, who's sleeping, who's waiting on some other function to kind of return, right? Like that's I think the real power. You can almost like query the distributed call stack, at least from the services that are on restate. Like if you have like a bunch of services on restate calling each other, you kind of can almost query the distributed call stack between them. And it's not that you're sort of maintaining the synchronous key, because it's just like an asynchronous index view, the whole thing. So Restate internally has a query engine based on Arrow Data Fusion, but the endpoint behind which we expose this actually speaks the Postgres wire protocol, so you can like use a Postgres client to query it. I actually haven't mentioned this before. Like, why data fusion makes sense for us because the server component is completely implemented in Rust. Actually, a big user of the Tokyo framework, which kind of fits very well with our philosophy. We have like this log, sort of single appender for the partition to the log. It kind of fits the Tokyo programming model pretty well. And being a Rust sort of system, Data Fusion just looked like a sort of promising Rust-based query execution engine that we connect to Postgres by, making Postgres. That we connect to RocksDB by making RocksDB sort of a virtual table that Data Fusion can scan and push certain predicates down to.
Yep. Okay, that's really cool. And do you anticipate that will be sort of that Postgres compatible endpoint there? Will that be something that is only used for like sort of occasional one-off hardcore debugging type thing? Or would that be something where I might have a dashboard open that's sort of continuously refreshing and just showing the state of my services and traffic and things like that going across? Like how often do you see that sort of that used?
It's a very good question. So at the moment, the biggest user of this is actually our own tools. Like the last version that you can actually find. I don't think it's actually officially published, but you can actually find the release artifacts already on GitHub on our website. The 0.7 version introduces a very, very powerful CLI that you can use to exactly examine the sort of status of services, like why is somebody waiting, how long has it been waiting for, who is it waiting for, and so on. That thing internally issues like a lot of queries to that system, right? That's the biggest user of that so far. You can use it to expose something about the state of your system in a dashboard. If you don't do it in a crazy aggressive way, like issue thousands of queries per second, might actually work. It's not at the moment optimized for like production workload queries. It's really more for like debugging, analysis, introspection type workloads. But it's a very interesting question. We've seen this being so valuable, and that we might actually do more work on this in the future to like make it sustain bigger loads. It's to be seen.
Yeah. Even if you had like a sort of like a read replica one, it's maybe just like pulling down the S3 data. Maybe it's a few seconds or however long behind, but you can query it and not worry about messing with your, the hot path of like these events getting appended and all that sort of stuff. But it just like gives you a look at your system and what's happening. That'd be kind of interesting, just to sort of see where that goes.
Yeah, that'd be very interesting. And again, like an LSM tree based architecture that you sort of like asynchronously write into, it's actually great because you can then create like different, you can have a different consumer pulling these artifacts and like running a query engine over this and so on. Lots of things are possible. Yeah.
Yeah. I've seen other tools doing that. Like Rockset has, they call it like compute separation, right? Where they're just pulling those down into different compute instances. So you don't have one query here messing with one query over there and stuff like that. So
yeah, makes total sense. I mean, Rockset is the folks that build RocksDB, so a lot of these things that we're thinking about, of course, they're also doing that. It just like kind of comes from using RocksDB. Yeah.
Yeah, cool. Let's talk about like where sort of Restate is, both like as a product and as a company and things like that. So like, is it in a state like where I can go out and sort of use it and start running stuff through it? Like, where are you at in sort of development cycle here?
Yeah. So there's different pieces that are in different stages. Like we have SDKs out there in TypeScript, JavaScript, Java Kotlin, that are there. They're pretty much good to go. There's the open source runtime that you can download. It's usable, but I would just add that it is still under like sort of rapid development, and it doesn't mean it eats your data. It's like I mentioned, we're actually pretty happy with the reliability so far, because I think that's like one of the things we get from this architecture that we have. That's sort of very simple, like single log paradigm. But we'll absolutely go through a few sort of iterations of the storage formats and everything. So if you're using it right now, like be aware, you might have to run a migration script at some point in time, when you upgrade. That's definitely a caution I would throw in. If you're happy with that, we'd be happy for you to check it out. We're also working on a cloud service which is in pretty early stages, and we're looking for folks that would be interested, like as sort of early like design partners for that. So open source, I would say, try it out as long as you're okay with like running migration down the road. Managed service, talk to us.
Yep, absolutely. Okay, so you sort of stopped working on Flink in 2021. Did you start on Restate right away, or like how long have you been working on Restate?
It depends a little bit when you count, right? Like these, some of the basic thoughts of it, we've been playing around for a while, sort of in the back of our heads. End of 2021, I left Flink. Actually took a longer parental leave in between, and I went really to work on Restate in the second half of 2022. We started by prototyping a lot. I would say the actual Restate development started kind of end of 2022, so a bit over a year ago.
Okay. And how big is you said we started working, like how big is the current team working on Restate?
Yeah, so we're 9.5 people, so not 9 people and somebody is 50%. We're still a fairly compact team, because we're iterating a lot on the foundation still, which I think works great in a small team.
Yep, cool. Are you based all over the world? I know you're in Germany, I believe. Are most people in Germany, or I guess where's the team based?
So I'm based in Germany. From the team is based sort of all around, mostly sort of European time zones or similar time zones at the moment. So we have some folks in the UK, Italy, South Africa, one person on the US East Coast. So somewhat all over the place, like we're working as a fully distributed company. But for the for the early days that we're in, we try to keep it in time zones that have enough overlaps so that when big discussions are necessary, we can actually get also in front of the screen for a while, or somebody might actually fly in and on relatively short notice, and we'll do a workshop and so on. So that's what we try to optimize for.
Very cool. Well, I just love learning about this. I love what you did with Flink, and have followed you on some of that stuff for a while. So it's cool to see this new project. If people want to know more about you or about Restate, where should they go to find you?
the Restate website maybe is the best first place to start. Restate.dev. We do have a Twitter account, also Restate Dev. I think those are the places that we usually where we usually share our stuff. I guess we're not young enough to have an Instagram account or something like this, but
yeah, that's all right. I don't either. So yeah, my kids maybe someday. So, but yeah, anyway, like, thanks for coming on the show. I love this stuff. I think it's super interesting, and thanks for like walking through like what's going on in that runtime and some of the distributed system stuff. I think it's really cool. So, best of luck to you and the team going forward. Excited to see this space continue to develop.
Oh, awesome. Yeah. Thanks so much for having me. It was a lot of fun. Thanks.
Cool.